This week we are working on Chapter 8, Regression. And so to begin with, not only can you compute the degree to which two variables are related to one another. For instance, last week when we computed correlations, you can also use these correlations to predict the value of one variable based on the value of another. This is a very special case of how correlations can be used, and it's a powerful tool for social and behavioral sciences researchers. So the basic idea is to use a set of previously collected data, such as data on variables x and y, calculate how correlated these variables are with one another, and then use that correlation and the knowledge of x to predict y. So let's talk more about how we can do this. For example, a researcher collects data on total high school grade point average, GPA, and first-year college GPA for 400 students in their freshman year at the state university, at UCA for instance. He computes the correlation between the two variables. Then he uses the techniques we'll learn about in a little bit to take a new set of high school GPAs, and knowing the relationship between high school GPA and first-year college GPA from the previous set of students, he predicts what first-year GPA should be for a new sample of 400 students. Here's another example where we could use a regression analysis. A group of teachers is interested in finding out how well retention works. That is, do children who were retained in kindergarten and not passed on to first grade do better in first grade? Once again, these teachers know the correlation between being retained and first grade performance from prior years. They can apply it to a new set of students and predict first grade performance based on kindergarten performance. So notice that with a regression, we are predicting, we are saying, we're trying to figure out if one variable is influencing another, is having an effect, is causing some type of effect on the other variable. This is different from correlation because last week we were only looking to see if there was a relationship between two variables. Now we are asking ourselves, is there a causal effect between the two variables? So how does regression work? Data are collected on past events, such as the existing relationship between two variables, and then it's applied to a future event, given knowledge of only one variable. The higher, so I want you to remember that correlation coefficient that you figured out that you computed in SPSS last week. It ranged from -1 to 0.1. Okay? And so the higher the absolute value of the correlation coefficient, so the higher the absolute value of it, the more accurate the prediction is of one variable from the other based on that correlation. Because the more two variables share in common, the more you know about the second variable based on your knowledge of the first. So going back to think about those scatter plots that we used last week, looking at whenever I had examples of the different correlation coefficients and how the higher that coefficient was, the more linear the data became. And so again, think about that regression line. The higher that correlation, the more linear it is, the more accurate that prediction of one variable will be to the other. So for instance, if a correlation is perfect, for instance, if you have a correlation of 1 or -1, the prediction is perfect as well. So if you know the value of x, then you can calculate the value of y. So let's look at the logic of prediction. So before we begin with the actual calculations and before I show you how correlations are used for prediction, let's understand the argument for why and how prediction works. And then we'll continue with the example of predicting college GPA from high school GPAs. So, prediction is the computation of future outcomes based on a knowledge of present ones. When we want to predict one variable from another, we need to first compute the correlation between those two variables, just like what we did last week. That was kind of like step one in the regression process. Now, notice this table 16.1. This goes back to the example I was talking about, high school GPA and first year college GPA. So this is the actual raw data. And if you look at this scatter plot, this is a scatter plot of the same data. It shows a scatter plot of the two variables that are being computed, the high school GPA and college GPA. So in order to predict college GPA from high school GPA, we have to create what's called a regression equation and use that to plot what we call a regression line. A regression line reflects our best guess as to what score on the y variable, which would be our college GPA, would be predicted by a score on the x variable, which would be our high school GPA. So, for all of the data that you see in table 16.1, the regression line is drawn so that it minimizes the distance between itself and each of the points on the predicted y variable. So here is our regression line right here. So what do you think that regression line represents? So first it's the regression of the y variable on the x variable. So in other words, y, which would be our college GPA, is being predicted from x, our high school GPA. Okay. How can we predict high school GPA? How can we predict our college GPA from our high school GPA? So this regression line is also called the line of best fit. The line best fits this data because it minimizes the distance between the individual point and the regression line. So for example, if you take all of these points and try to find the line that best fits them all at once, the line you would see in this figure right here would be the one that you would use. So what else does this regression line represent? It allows us our best guess, meaning it allows us to estimate what college GPA would be given each high school GPA. So for instance, let's look at this particular figure here, figure 16.3. So for instance, if there's a high school GPA of 3.0, then a college GPA should be around, and I'm only estimating, it will be around 2.8. So in order to do this, I located the predictor value. So if this is my predictor at GPA, remember you're trying to figure out, using a high school GPA, can I predict what that college GPA is? So if I am given a predictor of high school GPA of 3.0, I can use my regression line to then predict what would be the college GPA. And so this would be, I drew a perpendicular line from the x-axis to the regression line, and then drew a horizontal line to the y-axis, and then finally estimated what the predicted value of y would be, and it would be approximately 2.8. So what else does a regression line represent? The third thing that the regression line represents is the distance between each individual data point and the regression line, which is called the error in prediction. It's a direct reflection of the correlation between two variables. So for instance, looking at this particular correlation here, if you look at the data points 3.3 and 3.7, you can see that this occurs above that regression line. So the distance between this point and the line is called the error in prediction. Oops, sorry about that. The distance between this point and the regression line is the error in prediction, because if the prediction were perfect, then all of the predicted points would fall where? If it was a perfect correlation, it would all fall on this regression line. But it's not. It's not perfect. So this point falls above the regression line in this particular case. So again, if the correlation were perfect, all the data points would align themselves along a 45-degree angle, and the regression line would pass through each point. So how can we create a regression line? So the simplest way to think of a prediction is that you are determining the score on one variable, which we'll call y, which we can call our outcome or our dependent variable, based on the value of another score, which we'll call x, and that will be our predictor or our independent variable. So the way that we can find out how well x can predict y is through the creation of the regression line I mentioned earlier. So this line is created from data that have already been collected, and the equations are then used to predict scores using a new value for x, the predictor variable. Now I'm actually going to explain in detail the regression equation, because I think understanding the equation will help you have an easier time being able to interpret the data. If you can place those numbers, if you can connect those numbers with that equation and understand what they mean, I think the results of your regression analysis will make more sense. So here's the formula for the regression line. This is a general formula for the regression line. This is not the exact same formula that's used in the book, but it's actually the same concept. The only difference is that the symbols are different, but each part of the formula is the exact same. So this is the general formula for the regression line, and this may look familiar because you probably use something very similar in your high school and college math courses, and because it's the formula for any straight line. So y equals bx plus a. So y would be the predicted score of y, so I'm going to say y dash. Y dash is the predicted score of y based on a known value of x. B is our slope or direction of the line. A is the point at which the line crosses the y-axis. And then x is the score being used as the predictor. Okay? So let's look at some data. So this is the same data that we looked at earlier, but just with a few more calculations. And so as you can see the totals here. And so from this table, we can see sigma x, and sigma is a Greek symbol that means summation. So basically, we say sigma x, or we can say the sum of all the x values is 31.4. So the sum of all of our x values is 31.4. The sum of all of our y values is 29.3. The sum of all of our x squared values is 102.5. The sum of all of our y square values, our y value squared, is 89.99. And the sum of all of our xy values is 94.75. Now, in order to compute the slope of the regression line, we want to compute b. This would be, we would use the summation of xy, going back to that column that was given here, the summation of xy, that 94.75. So we're looking at the summation of xy minus the summation of x times the summation of y divided by n. Now n would be your sample size. Our sample size here is 10. Okay, this would be divided by the summation of x squared minus the summation of x squared divided by n. And so when we actually plug in our numbers from our table, this would give us a slope of 0.704. Now this is the formula we would use to compute the point at which the line crosses the x-axis. So we have our a equals summation of y minus our slope. So we'll have to use our slope number that we just calculated minus the slope times the summation of x divided by n, which would be our sample size. So again, we can plug in our numbers, 29.3 minus, and here's our slope value that we calculated, times 31.4 divided by 10, and this would give us an A of 0.719. So now, if we go back and substitute B and A into our equation for a straight line, we would come up with the final regression line of y dash equals 0.704x plus 0.719. So now, based on this, if this is what, we can use this to figure out in order to predict y. So we would say, so let's say that high school GPA equals 2.8, or x would equal 2.8. So we had our equation here, and if we were given what x is, a GPA of 2.8, we can substitute the value of 2.8 into the equation, and we would getting the following formula. And so 2.69 would be the predicted value of y given x is equal to 2.8. So basically, if a student has a high school GPA of 2.8, it's predicted that that individual would have a college GPA of 2.69. So regression analysis is a parametric test. And so there are certain assumptions that must be met in order for before we can complete a regression analysis. And so these are the various assumptions. And so the first assumption would be that our variables must be continuous. They should be at the continuous level, and this could be either interval variables or ratio variables. This could be, examples could be revision time, measured in hours, or intelligence, measured using an IQ score, or an exam performance, measured from 0 to 100, weight, measured in kilograms, and so forth. Another assumption is that there should be a linear relationship between the two variables. So here are two examples of, it could be either a positive relationship or a negative relationship. And this illustration right here shows no linear relationship. So again, the higher that correlation coefficient, the more likely that there is some type of causal effect, and so it's possible that you can run a regression analysis on that. Because remember, the higher that coefficient, the more linear relationship your two variables will have. Another assumption is that there shouldn't be any significant outliers. So whenever you are testing for linearity, you can easily determine if there are any outliers. For instance, this would be an outlier, this would be an outlier. So if you have any significant outliers, either it's probably best to take out that outlier, because if not, it'll definitely skew your data. So you can possibly take out that one or two outliers, and then you can run your regression analysis. Another assumption should be there should be an independence of observations. So meaning that each person, each individual in your sample, you should only collect data from that person once and only once. There shouldn't be any type of, you shouldn't be collecting data from one person more than one time. All of the data should be independent of each other. Another assumption is that make sure that there are residuals, that the residuals are approximately normally distributed. So the errors of the regression line are normally distributed. And finally, we have I can't say it tonight, I'm so sorry. Homoscedasticity. And here are illustrations of what this would look like on a graph to show you what homoscedasticity should look like. And these are the various assumptions of your regression analysis. And the next part of your class lecture, I will focus on an actual example using SPSS. Thanks so much.